All right, let's go ahead and get started. Oh, hello. Hello. Hmm. Hello. Okay. That's so weird. Oh, I see. Yep. Oh. Okay. I wasn't sure where my. All right. I get it now. Okay. I'm still getting used to ops. I'm not uh, that familiar with the software, but you know. So today, I think we're just gonna keep reading the Russ Lang book, the book, as they call it. Error handling. This is going to be pretty boring, I think, but it looks really short, so we'll just zoom right past it. Error handling. Rust's commitment to reliability extends to error handling. Errors are, in fact, uh, hold on, let me put my phone do not disturb. Um, let's see. In many cases, Rust requires you to acknowledge the possibility of an error and take some action before your code will compile. This requirement makes your program more robust by ensuring that you'll discover errors and handle them appropriately before you've deployed your code to production. Rust groups errors into two major categories: recoverable and unrecoverable. For a recoverable error, such as a file not found error, it's reasonable to report the problem to the user and retry the operation. Unrecoverable errors are always symptoms of bugs, like trying to access a location beyond the end of an array. Most languages don't distinguish between these two kinds of errors and handle both in the same way using mechanisms such as exceptions. Rust doesn't have exceptions. Instead, it has the type result TE for recoverable errors and the panic macro that stops execution when programs encounter unrecoverable errors. This chapter will cover calling panic first and then talk about returning result TE values. Additionally, we'll explore considerations when deciding whether to try to recover from error or stop execution. Unrecoverable errors with panic. Sometimes bad things happen in your code, and there's nothing you can do about it. In these cases, Rust has the panic macro. When the panic macro executes, your program will print a failure message, unwind and clean up the stack, and then quit. We'll commonly invoke a panic when a bug of some kind has been detected and it's not clear how to handle the problem at the time we're writing our program. Unwinding the stack or aborting in response to a panic. By default, when a panic occurs, the program starts unwinding, which means Rust walks back up the stack and cleans up the data from each function it encounters. However, this walking back and clean up is a lot of work. Rust therefore allows you to choose the alternative of immediately aborting, which ends the program without cleaning up. Memory that the program was using will then need to be cleaned up by the operating system. If in your if in your project you need to make the results binary as small as possible, you can switch from unwinding to aborting upon a panic by adding panic equal abort in the appropriate profile section in your cargo.toml file. For example, if you want to abort on panic in release mode, add this profile.release. Excellent. That's easy. Let's try calling panic in a simple program. So this is main, and the only thing in here is panic, crash, and burn. when you run the program, you'll see something like this: cargo run, and then running main thread main panic at crash and burn. Note that the usual. The call to panic causes the message contained in the last two lines. The first line shows our panic message, and the place in the source code where the panic occurs indicates that this is the second line, fifth character of our main.rs file. In this case, the line indicates that part of the code, and if we go into that line, we see the panic macro call. In other cases, the panic macro call might be in code that our code calls, and the file name and line number reported by the error message will be someone else's code where the panic macro is called, not the line of our code that eventually led to the panic call. We can use the backtrace of the function the panic macro call came from to figure out the part of our code that is causing the problem. We'll discuss backtraces in more detail next. I will minimize this a little bit. So, oops, that's not the right one. Okay, there's that part, but I want, there you go. Since I messed up my resolution, almost got it. It was like 4, what? Okay. I guess 1924 by 1080 is close enough. Okay. Let's see. Using a panic backtrace. Let's look at another example, see what it's like when a panic call comes from the library because of a bug in our code instead of from a code calling the macro directly. Listing 9.1 has some code that attempts to access an index in a vector beyond the range of the index. So I've had the panic happen to me just from experimenting, so I feel like I'm familiar with this to some extent, but we'll keep reading. Let's see. So there's only 3 spots, but we're calling for spot 99. So we're attempting to access the 100th element of the vector, which is index 99 because indexing starts at 0, but a vector has only 3 elements in this situation. Rust will panic using brackets to using brackets is supposed to return an element, but if you pass an invalid index, there's no element that Rust could return here that would be correct. Excuse me. And C, attempting to read beyond the end of the data structure is undefined behavior. You might get whatever is at that location in memory that would correspond to the element in the data structure, even though the memory doesn't belong to that structure. This is called a buffer overread and can lead to a security vulnerability if the attacker is able to manipulate the index in such a way as to read data they shouldn't be allowed to, that is stored after the data structure. To protect your program from this sort of vulnerability, if you try to read an element and an index that doesn't exist, Rust will stop execution and refuse to continue. Let's try it and see. Panic at index out of bounds. The len is 3, but the index is 99. Yep. The error point at line 4 of our main RS when we try to access index 99, the next note line tells us that we can set the Rust backtrace environment variable to get the backtrace of exactly what happened to cause the error. The backtrace is a list of all the functions that have been called to get to that point. Backtrace in Rust works as they do in other languages. The key to reading a backtrace is to start from the top and read until you see files you wrote. That's the spot where the problem originated. The lines above that spot are code that your code has called. The lines below the code that called your code. These before and after lines might include core Rust code, standard library code, or crates that you're using. Let's try getting a backtrace by setting the Rust backtrace environmental variable to any value except 0. So you set it first and then you run cargo run. Then you begin unwind. Then the core is panicking. You size at core slice index, vect t, because you're using a vector, panic main. So there it is right there. It's a lot of output. The exact output you might see is different depending on your operating system and Rust version. In order to get backtraces from this information, debug symbols must be enabled. Debug symbols are enabled by default when using cargo build or cargo run without the release flag, as we have here. The output in listing 9.2, line 6 of the backtrace point to the line in our project that's causing the problem. Line 4 of main RS. If we don't want our program to panic, we should start our investigation at the location pointed to by the first line mentioning a file that we wrote, where we deliberately wrote code that would panic. The way to fix the panic is to not request an element beyond the range of the vector indexes. When your code panics in the future, you'll need to figure out what actions the code is taking with what values to cause the panic and what the code should do instead. We'll come back to panic and when we should and should not use panic to handle errors. Conditions in the to panic or not to panic section. Okay. Yep. All right, recoverable errors and result. Most errors aren't serious enough to require the program to stop entirely. Sometimes when a function fails, it's for a reason that you can easily interpret and respond to. For example, if you try to open a file and that operation fails because the file doesn't exist, you might want to create the file instead of terminating the process. Recall that handling potential failures with result type in chapter 2, that the result enum is defined as having two variants, OK and error. Yep, OK, error. T and E. Excuse me. T and E are generic type parameters. We'll discuss generics in more detail in 10. What you need to know right now is that T represents the type of the value that will be returned in a success case with the OK variant, and E represents the type of the error that will be returned in a failure case within the error variant. And because result has the generic type parameter, we can use the result type and the functions defined on it in many different situations where the successful value and error value we want to return may differ. Let's call a function that returns a result value because the function could fail. In listing 9.3, we try to open a file. Okay. How do we know file open returns a result? We could look at the standard library API documentation, or we could ask the compiler. If we gave f a type annotation that we know is not the return type of the function, and then we try to compile the code, the compiler, I can't stop yawning. The compiler will tell us that the types don't match. Yep. The error message will then tell us that the type of F is, let's try it. We know that the return type of file open isn't the type U32, so let's change the let F statement to this. Okay. Attempting to compile now gives us the following output. Yeah, he expects the U32. This tells us the return type of the file open function is a result TE. The generic parameter T that has been filled in here with the type of the success value, standard library FS file, which is a file handle. The type of E used in the error value is stdio error. The return type means that the call to the file open might succeed and return a file handle, and we can read or write to the function call also might fail. For example, the file might not exist, or we might not have permission to access the file. The file open function needs to have a way to tell us whether it succeeded or failed. At the same time, give us either the file handle or error information. This information is exactly what the result enum conveys. Okay. In the case where a file open succeeds, the value of the variable f will be the instance of OK that contains a file handle. In the case where it fails, the value of f will be the instance of error that contains more information about the kind of error that happens. We need to add to the code to take different actions depending on the value file open returns. Listing 9.4 shows one way to handle result with using a basic tool, the match expression we discussed in chapter 6. So you do file open, and then you can do a let f match f OK file. Yeah, so if OK is a file, then you return the file, and if error is an error, you return the panic with the all the error information, I guess. Note that the option enum, the result enum, and its variants, they use the Oxford comma here, or they don't use an Oxford comma. That's funny. Maybe they're British. Is that a British thing? I don't know. I don't want to stereotype who uses an Oxford comma. And its variants have been brought into scope by the prelude, so we don't need to specify result ... before we open before the OK and the error variants in the match arm. When the result is OK, the code will return the inner file value out of the OK variant, and what we then assign the file handle value to the variable f after the match, and can use the file handle for reading or writing. The other arm of the match handles the case where we get an error value from the file open. In this example, we've chosen to call the panic macro. It's if there's no file named hello text in our current dictionary directory, and we run this code, we'll see the following output from the panic macro. And it's just the it's just the way you put in the macro. Yep. Okay. Matching on different errors. So the code in listing 9.4 will panic no matter why file open failed. However, we want to take different actions for different failure reasons. If file open failed because the file doesn't exist, we want to create the file and return the handle to the new file. file open failed for any other reason, for example, because we don't have permissions to open the file, we still want the code to panic in the same way as it did in listing 9.4. For this, we need to add an inner match expression shown in listing 5.9. So same code up until here, and then there's a error, and then error.kind, match error.kind, and then here you need to do error kind with the double colon not found for so right, that's the code is not found. If it's not found, then you create the file, and and then there's another error handling here for the newly created txt, and that's an OK and an error, and then another error for the panic if it doesn't match the not found scenario. Okay, easy peasy. I guess other error is generic. The type of the value that file open returns inside the error variant is IO error, which is a struct provided by the standard library. This struct has a method kind that we can call to get an IO error kind value. The enum IO error kind is provided by the standard library and has variants representing different kinds of errors that might result from an IO operation. The variant we want is error kind not found. So we had to import that, which indicates the files we're trying to open doesn't exist yet. So we match on F, but we also have an inner match on error kind. The condition we want to check in the inner match is whether the value returned by error kind is not found, is the not found variant of error kind. If it is, we try to create the file with the file create. However, because file create could also fail, we need a second arm in the inner match expression. When a file cannot be created, a different error message is printed. The second arm of the outer match says the same, so the program panics on any error besides the missing file error. Alternatives to using match with result. That's a lot of match. The match expression is very useful, but also very much a primitive. In chapter 13, you'll learn about closures, which are used with many of the methods defined in result. These methods can be more concise than using match when handling result values in your code. For example, here's another way to write the same logic as shown in 9.5, but using closures and the unwrap or else. Okay, and so file open, and then here's unwrap or else, and then inside you have the error bracket if error.kind equal error kind not found. You do this, and then that has a or else panic, and then here, yeah, okay, so you try it, you unwrap it, or else here's the error, and then you can pass that error into a panic. It's like an if statement. Although the code has the same behavior, it doesn't contain any match expressions and is cleaner to read. Come back to the example after you've read chapter 13 and look up the unwrap or else method in the standard library documentation. Shortcuts for panic or error, unwrap, and expect. Using match works well enough, but it can be a bit verbose and doesn't always communicate intent well. The result TE type has many helper methods defined on it to do various more specific tasks. The unwrap method is a shortcut method implemented just like the match expression we wrote in 9.4. If the result value is OK variant, unwrap will return the value inside the OK. If the result is an error variant, unwrap will call the panic macro for us. Here's an example of unwrap in action. So that just returns hello, but without an error. If we run this code, we'll see an error message from the panic call that the unwrap method makes. No such file or directory. Similarly, the expect method lets us choose the panic error message using expect instead of unwrap, and providing good error messages can convey your intent and make tracking down the source of panics easier. The syntax of expect looks like this. Expect failed to open hello text. We use expect in the same way as unwrap to return the file handle or call the panic macro. The error message used by expect is its call to panic. Used by expect in its call to panic will be the parameter that we pass to expect rather than the default panic message that unwrap uses. Here's what it looks like. Because this error message starts with the text we specified, failed to open hello txt, it will be easier to find where in the code this error message is coming from. If we use unwrap in multiple places, it can take more time to figure out exactly which unwrap is causing the panic, because all unwraps call the panic print the same message. I see. So it's better to use expect. I've been using unwrap. And I didn't know that's what it did. I didn't know it was an error handling tool. That's good. Let's see. Propagating errors. When a function implementation calls something that might fail, instead of handling the error within the function itself, you can return the error to the calling code so that it can decide what to do. This is known as propagating the error and gives more control to the calling code, where there might be more information or logic that dictates how the error should be handled than what you have available in the context of your code. For example, listing 9.6 shows a function that reads a username from a file. If the file doesn't exist or can't be read, this function will return those errors to the code that called the function. Okay, that's kind of weird. So here's a function, result string, and then error. You open your txt. If f matches f, OK file, and then you can return your error. And then here you have a string, and if f dot read to string, okay, and then you pass as this string, OK s, return s e error. I don't really see how that's different than what you've been doing. I guess, yeah, I'm not sure how that's different. Let's see. I'm not sure what this underscore is. This function can be written in a much shorter way, but we're going to start by doing a lot of it manually in order to explore error handling. At the end, we'll show the shorter way. Looks like let's look at the return type in the function. Okay, this seems typical to me. Your results either return the string or the error. That's what they've been saying. This means that the function is returning the value of result te, where the generic parameter t has been filled in with the concrete type string, and the generic type e has been filled in with the concrete type io error. If this function succeeds without any problem, the code that calls this function will receive an OK value that holds a string, the username, that this function reads from the file. If this function encounters any problem, the calling code will receive an error value that holds an instant of IO error that contains more information about what the problems were. We choose IO error as a return type of this function because that happens to be the type of the error value returned from both of the operations we're calling in this function's body that might fail, the file open function and the read to string method. The body of the function starts by calling the file open function. Then we handle the result value with a match similar to the match in listing 9.4. If file open succeeds, the file handle in the pattern variable file becomes the value in the mutable variable f. I'm so lost. Hold on a second. Okay, so this makes sense. Okay, the body of the function starts by calling the file open function. Yes. Okay, we handle the result value with a match similar to the match. Yeah. If file open succeeds, then the file handled in the pattern variable file becomes the value of the mutable variable f. Yeah. Okay. If this succeeds, then this becomes f. Okay, and then in the case of error, we panic. We use the return keyword to return early out of the function entirely and pass the error value from file open. Now the pattern variable e back to the calling code as the function's error value. So if the file in f, the function that creates the string in variable s and calls the read to string method of the file handled in f to read the contents of the file in s. The read to string method also returns a result that might fail. Even though file open succeeds, we still need another match to handle the results. If read to string succeeds, then our function has succeeded and returned the username from the file that's now in s wrapped in an OK. If read to string fails, we return the error value in the same way that we returned the error value in the match that handled the return value of file open. However, we don't need to say explicitly return because it's the last expression of the function. The code that calls this code will then handle getting either OK value that contains the username or error that contains an error. It's up to the calling code to decide what to do with those values. If the calling code gets an error value, it can call panic and crash the program, use a default username, or look up the username from somewhere other than a file. For example, we don't have enough information on what the calling code is actually trying to do, so we propagate all the success or error information upward for it to handle appropriately. The pattern of propagating errors is so common in Rust that Rust provides the question mark operator to make them easy. Okay. I mean, this seems just like what we did here, except in two files or two functions. 9.7 shows an implementation of read username from file. It has the same functionality as in 9.6, but implemented using the question mark. So, same thing. You have the open, you have a new string, and here we have f.readToString, and then here's the s, and then you do a question mark. The question mark placed after a result value is defined to work in almost the same way as the match expression we defined to handle the result value in listing 9.6. If the value of the result is an OK, the value inside the OK will return from this expression, and the program will continue. If the value is an error, the error will be returned in the whole function as if we had used the return keyword, so the error value gets propagated to the calling code. There is a difference between what the match expression from 9.6 does and what the question mark operator does. Error values that have the question mark operator called on them go through the from function defined in the from trait in the standard library, which is used to convert errors from one type into another. When the question mark operator calls the from function, the error type received is converted into the error type defined in the return value of the current function. This is useful when a function returns one error type to represent all the ways a function might fail, even if parts might fail for many different reasons. As long as there's an implement from other errors for returned error to define the conversation in the traits from function, the question mark operator takes care of calling the from function automatically. In the context of 9.7, the question mark at the end of the file open call will return the value inside an OK to the variable f. If an error occurs, the question mark operator will return early out of the whole function and give any error value to the code. The same thing applies to the question mark at the end of the read to string call. The question mark operator eliminates a lot of boilerplate and makes the function's implementation simpler. You could even shorten this code further by chaining method calls immediately after the question mark, as shown in 9.7. Oh, I see. Okay, yeah. Okay. Yeah, okay. We've moved the creation of the new string in S to the beginning of the function. That part hasn't changed. Instead, the creating a variable f, we've chained the call to read string directly onto the result of the file open. We still have the question mark at the end of the read to string call, and we still return an OK value containing the username in S when both file open and read to string succeed rather than returning errors. Functionality is again the same as in 9.6, 9.7. This is just a different, more ergonomic way to write it. 9.9. Um, Reading a file into a string is a fairly common operation, so the standard library provides the convenient fs read to string function that opens the file, creates a new string, reads the contents of the file, puts the contents into the string, and returns it. Of course, using fs read to string doesn't give us the opportunity to explain all the error handling, so we did it the long way first. He doesn't have a question mark at the end of this, where the question mark operator can be used. The question mark operator can only be used in functions whose return type is compatible with the value the question mark is used on. This is because the question mark operator is defined to perform an early return of a value out of a function in the same manner as the match expression as defined in 9.6. In 9.6, the match was using a result value, and the early return arm returned an error E value. The return type of the function has to be a result so that it's compatible with the return. In listing 9.10, let's look at the error we'll get if we use the question mark operator in a main function with a return type incompatible with the type of value used on question mark. So there's no return type. The code opens the file, which might fail. The question mark operator follows the result value returned by file open, but this main function has the return type of unit, not result. When we compile this code, we get the following error. I recently learned that this is called unit, so I had to emphasize it. Let's see. Yep, cannot use question mark. The function should return result or option to accept question mark. This error points out that we're only allowed to use the question mark operator in a function that returns result option or another type that implements from residual. To fix the error, you have two choices. One choice is to change the return type of your function to be compatible with the value you're using the question mark operator. So as long as you have no restrictions preventing that, the other technique is to use match or one of the result TE methods to handle the result TE in however way is appropriate. The error message also mentioned that question mark can be used with option T values as well as with using question mark on result. You can use question mark on option in a function that returns an option. The behavior of the question mark operator when called on an option T is similar to its behavior when called on a result TE. The value is none. The none will be returned early from the function at that point. If the value is sum, a value inside the sum is the resulting value of the expression, and the function continues. Listing 9.11 has an example of a function that finds the last character of the first line in the given text. So text, which is passed into the function, and it returns an option character dot lines dot next dot, and that's a question mark dot characters dot last. This function returns option character because it's possible that the character that there is a character there, but it's also possible that there isn't. The code takes the text string slice argument that calls the lines method on it, which returns an iterator over the lines in the string. Because the function wants to examine the first line, it calls next on the iterator to get the first value from the iterator. If text is an empty string, this call to next will return none, in which case we use question mark to stop the return none from last character of the first line. If text is not the empty string, next we'll return the sum value containing a string slice of the first line in the text. The question mark extracts the string slice, and we can call characters on the string slice to get an iterator of its characters. We're interested in the last character of the first line, so we can call last to return the last item in the iterator. This is an option because it's possible that the first line is the empty string. For example, if text starts with the blank line that has characters on other lines, as in /ni. However, if there is a last character on the first line, it will return in the sum variant. The question mark operator in the middle gives us a concise way to express this logic, allowing us to implement the function in one line. If we couldn't use the question mark operator on option, we'd have to implement the logic using a more methods called or match expression. Note that you can use the question mark operator on a result in a function that returns result. You can use the question mark operator on an option in a function that returns option, but you can't mix and match. The question mark operator won't automatically convert a result to an option or vice versa. In those cases, you can use methods like OK method on result or OK or method on option to do the conversion explicitly. So far, all the main functions we've used return unit. The main function is special because it's the entry and exit point of the executable program, and there's a restriction on what its return types can be for the programs to behave as expected. Luckily, main can return a result T unit E. Result unit E, listing 9. So you can return unit or error. But we've changed the return type of main to be result unit box dyn error and added a return value OK to the end. This code will compile. Box dyn error is a trait object, which we'll talk about using trait objects that allow for values of different types. Section in 17. For now, you can read box dyn error to mean any kind of error using question mark on a result value in the main function with error type box dyn error is allowed because it allows any error value to be returned early. When the main function returns a result unit E, executable will exit with the value of 0 if main returns OK, and will exit with a non-zero value if main returns an error value. Executables written in C return integers when they exit. Programs that exit successfully return the integer 0, and programs that error return some integer other than 0. Rust must also returns integers from executables to be compatible with this convention. The main function may return a value that implements the standard process termination trait. As of this writing, the termination trait is an unstable feature only available in nightly Rust, so you can implement it for your own types in stable Rust, but you might be able to you can't yet implement it in stable Rust, but you might be able to someday. Now we'll discuss in detail calling panic or returning a result. Let's return to the topic of how to decide which is appropriate use in which case. Okay, this one is fairly short, and I think I'll close up after this chapter. I thought I was going to be able to last till 10, but reading about errors is just, I need a break after that. To panic or not to panic. So how do you decide when you should call panic and when you should return result? When code panics, there's no way to recover. You can call panic for any error situation, whether there's a possible way to recover or not. But then you're making a decision that a situation is unrecoverable on behalf of the calling code. When you choose to return a result value, you give the code options. The calling code can choose to attempt to recover in a way that's appropriate for its situation, or it could decide that an error value in this case is unrecoverable. So it can call panic and turn your recoverable error into an unrecoverable error. Therefore, returning a result is a good default choice when you're defining a function that might fail. In situations such as examples, prototype code, and tests, it's more appropriate to write code that panics instead of returning a result. Let's explore why, then discuss situations in which the compiler can't tell that failure is impossible, but you as a human can. The chapter will conclude with some general guidelines on how to decide whether to panic in a library code. When you're writing an example to illustrate some concept, also include robust error handling code can make the example less clear. In examples, it's understood that a call to a method like unwrap that could panic is meant as a placeholder for the way you'd want your application to handle errors, which can differ based on what the rest of your code is doing. Similarly, the unwrap and expect methods are very handy when prototyping before you're ready to decide how to handle errors. They leave clear markers in your code for when you're ready to make a program more robust. If a method call fails in a test, you'd want the whole test to fail even if the method isn't the functionality under test. Okay, yep. Because panic is how a test is marked as a failure, calling unwrap or expect is exactly what should happen. Cases in which you have more information than the compiler. Cases in which it would be appropriate to call unwrap when you have some other logic that ensures that the result will have an OK value, but the logic isn't something the compiler understands. You'll still have a result value that you need to handle. Whatever operation you're calling still has the possibility of failing in general, even though it's logically impossible for your particular situation. If you can ensure by manually inspecting the code that you'll never have an error variant, is perfectly acceptable call unwrap. Here's an example. You're always going to parse the local host because it's just local host. So you can unwrap it. You know that parse is always going to work. We're creating an IP address instance by parsing a hard-coded string. We see that localhost is a valid IP, so it's acceptable to use unwrap here. However, having a hard-coded valid string doesn't change the return type of the parse method. We still get a result value, and the compiler will still make us handle the result as if the error variant is a possibility, because the compiler isn't smart enough to see that the string is always a valid IP address. If the IP address string came from a user rather than being hard-coded into the program and therefore did have a possibility of failure, we definitely want to handle the result in a more robust way instead. Guidelines. It's advisable to have your code panic when it's possible that your code could end up in a bad state. In this context, a bad state is when some assumption, guarantee, contract, or invariant has been broken, such as when invalid values, contradictory values, or missing values are passed in your code, plus one or more of the following. The bad state is something that is unexpected or as opposed to something that will likely happen occasionally, like using a user entering data in the wrong format. Your code after this point needs to rely on not being in a bad state rather than checking for the problem at every step. There's a good way to encode this information in types you use. We'll work through an example of what we mean in encoding behaviors as types. If someone calls your code and passes in values that don't make sense, the best choice might be to call panic. The alert the person using your library and the bug in their code, and alert the person using your library to the bug in their code so that they can fix it during development. Similarly, panic is often appropriate if you're calling external code that is not in your control and it returns an invalid state that you have no way of fixing. However, when failure is expected, it's more appropriate to return a result rather than to make a panic call. Examples include a parser being given malformed data, or an HTTP request returning a status that indicates you have hit a rate limit. In these cases, returning a result indicates that failure is an expected possibility and that the calling code must decide how to handle. When your code performs operations on values, your code should verify that the values are valid first and panic if the values aren't valid. This is mostly for safety reasons. Attempting to operate on invalid data can expose your code to vulnerabilities. This is the main reason the standard library will call panic if you attempt an out-of-bounds memory access. Trying to access memory that doesn't belong to the current data structure is a common security problem. Functions often have contracts that their behavior is only guaranteed if the inputs meet particular requirements. Panicking when the contract is violated makes sense because the contract violation always indicates a caller side bug, and it's not the kind of error you want the calling code to have an explicitly handle. In fact, there's no reasonable way for calling code to recover. The calling programmer need to fix the code. Programmers need to fix the code. Contracts for a function, especially when a violation will cause a panic, should be explained in the API documentation for the function. However, having lots of error checks in your functions would be verbose and annoying. Fortunately, you can use Rust type system and thus the type checking done by the compiler to do many of the checks for you. If your functions have a particular type as a parameter, you can proceed with your code's logic, knowing that the compiler has already ensured you have a valid value. For example, if you have a type rather than an option, the program expects to have something rather than nothing. Your code that doesn't have to handle two cases for some and none variants. It will only have one case for definitely having a value. Code trying to pass nothing to your function won't even compile, so your function doesn't have to check for that case at runtime. Another example is using an unsigned integer type such as U32, which ensures the parameter is never negative. Creating custom types for validation. Let's take the idea of using Rust type systems to ensure we have a valid value one step further and look at creating a custom type for validation. Calling the guessing game in chapter 2, in which our code asks the user to guess a number between 1 and 100, we never validated that the user's guess was between those numbers before checking it against our secret number. We only validated that the guess was positive. In this case, the consequences were not very dire. Our output of too high or too low would still be correct, but it would be a useful enhancement to guide the user toward a valid guess and have different behavior when our user guesses a number that's out of the range versus when the user types, for example, letters instead. One way to do this is would be to parse the guess as a I32 instead of only a U32 to allow potentially negative numbers, and then add a check for the number being in the range. So um, yeah, so if expression check whether our value is out of range tells the user about the problem and calls continue to start the next iteration of the loop and ask for another guess. If after the if expression we can proceed with the comparison between guess and the secret number, knowing that the guess is between 1 and 100. However, this is not an ideal solution. If it was absolutely critical that the program only operated on values between 1 and 100, it had many functions, and it had many functions with this requirement. Having a check like this in every function would be tedious and might impact performance. Instead, we can make a new type and put the validations in a function to create an instance of a type rather than repeating the validations everywhere. That way, it's safe for functions to use the new type in their signatures and confidently use the values they receive. And listing 913 shows one way of defining a guess type that will only create an instance of guess if the new function receives a value of 1 and 100. New value I32 is the guess. Oh, yeah, implement. First, we define the struct named guess that has a field named value that holds an I32. This is the number where the number will be stored. Then we implement an associated function named new on guess that creates an instance of guess value. The new function is defined to have one parameter named value of type I32 and to return a guess. The code in the body of the new function tests value to make sure it's between 1 and 100. If value doesn't pass this test, we make a panic call, which will alert the programmer who is writing the code that they have a bug they need to fix, because creating a guess with a value outside this range will violate the contract that guess new is relying on. The condition in which guess new might panic should be discussed in its public-facing API documentation. We'll cover documentation conventions indicating the possibility of a panic in the API documentation that you create in Chapter 14. If value does pass the test, we create a new guess with its value field set to the value parameter and return the guess. Next, we implement a method named value that borrows self, doesn't have any other parameters, and returns an I32. This kind of method is sometimes called a getter because its purpose is to get some data from the field and return it. The public method is necessary because the value from the guess struct is private. It's important that the value field be private, so code using guess struct is not allowed to set values directly. Code outside the module must use the guess new function to create an instance of guess, thereby ensuring there's no way for a guess to have a value that hasn't been checked by the conditions in the guess new function. A function that has a parameter or returns only values between 1 and 100 could then declare in its signature that it takes or returns a guess rather than an I32 that wouldn't need to do any additional checks in its body. Rust error handling features are designed to help you write more robust robust code. The panic exclamation point macro signals that your program is in a state it can handle and lets you tell the process to stop instead of trying to proceed with invalid or incorrect values. The result enum uses Rust types system to indicate that operations might fail in a way that your code could recover from. You can use result to tell code that calls your code that it needs to handle potential success or failure as well. Using panic and result in the appropriate situation will make your code more reliable in the face of inevitable problems. Now that you've seen useful ways that the standard library uses generics, with the option and result enums, we'll talk about how generics work and how you can use them in your code. Well, all right. Well, errors were fun. I'm going to end it there. I'll see you guys.